Hi students, this video we're going to be looking at graphing nth degree polynomials, and so we're just going to kind of dive right into it. So when I say an nth degree polynomial, that means if you were to write in standard form, you would write in like a decreasing degree of the x values there, the x exponents. So like for instance, 3x cubed minus 5x squared plus x minus 1 would be an example of like just a polynomial in standard form. It doesn't have to be in standard form. There's some more useful forms for us out there, but that's what we mean by just like an nth degree polynomial, just kind of like that decreasing standard form polynomial. So there's a couple of features that we can just sort of notice right away when we're talking about polynomials, and that's even degree polynomials are kind of all the same vibes as parabolas, if you want to think about it like that, because a parabola still is an even degree polynomial. So an even degree polynomial is always going to either open up or open down. Okay, so there might be some stuff happening in the middle, and we'll figure out how to find out that stuff here in a second. But essentially, it's always going to be opening up or opening down together. They do not necessarily have x-intercepts. So for instance, if it's opening down, because they open down or up, you can translate them high enough or low enough so that the curve does not touch the x-axis. And yeah, so those are even degree polynomials, like their general features in a nutshell. Odd degree polynomials are just basically like have the same behavior as a straight line, because a line is still an odd degree polynomial. Like y equals x is a polynomial and the power of x is odd. And to be clear, I should be even clarifying this language. When I say even degree, that means when you look at the highest power possible, it's going to be an even number. So for instance, if I look up here, this cubic function would be an odd degree polynomial because the highest power of x I see is this x cubed. And this function right here, this part of our equation, is what dictates the behavior of the general curve, because cubing x is going to have a much greater impact than squaring x, than evaluating x, or even subtracting some constant or adding some constant. This right here is the driver of the behavior. Okay, and so to go back to this, odd degree polynomials, they zigzag. Okay, so they're going to zigzag like this, or they're going to zigzag like that. All right, and the amount of zig and zagging going on is going to be influenced by their actual inputs, the transformations going on. Sometimes they'll zig and look quite boring and do kind of this, like the lazy zig and zag. And finally, they're always going to have an x-intercept because they zigzag from infinity to negative infinity or vice versa. That means they have to cross an x-axis. No matter where I put it, it'll cross it at least once. And by extension, actually, they have no restriction to their range either. Whereas, in case this wasn't clear, there is going to be some restriction to the range where it'll be y is less than some value here, or y is greater than some value there. Just like a parabola. Okay, it all boils down to a parabola, or like the kind of the vibes of the parabola. So when we're graphing these at this level, they're going to be presented primarily in standard form or in factored form, or you're going to be able to easily get to factored form. So when we look at these in factored form, just a little reminder, you've been graphing in factored form with quadratic. So like if I said, hey, quadratic in factored form is x minus 1, x plus 2, you would say, oh, there's x-intercepts at 1 and 2. And then you could say, all right, I know I've got an x-intercept there. Oh, sorry, oh my goodness, an x-intercept here. Wow, an x-intercept there. That should be negative 2. Look at that. It looks like negative 2. It looks like this. And you can even say, hey, I know the quadratic opens up, so it must look something like that. And you knew it would open up, by the way, because there's no negative in front. And we're just going to take this, we're going to extrapolate this, right? Like if I have a series of x-intercepts in a row, and they're just kind of generic, nothing's being squared, or there's no coefficients, well, I can just say, hey, x-intercept at 1, x-intercept at x2, x-intercept at x to the n, and I can make note of all those points and just draw my curve going through them, okay? There is some behavior here that we want to note, that when we have even degree exponents there, what we have happening is we're going to have a bounce at the intercept, so it bounces. Okay, so it doesn't matter whether we're talking about 2 or 4 or 10 or 100. What you would see happening at the intercept is it will hit the intercept and bounce off. Okay, and that might lead to some of you saying, okay, what's the material difference of 1 versus 3, or 2 versus 4, or 1 versus 100 for that matter, or 3 versus 100, or not 100, so like 99. So how could you realistically tell the difference from one to the other? To actually find what it is, you would have to be given more points and evaluate and check. or be told explicitly what a stretch is, and then you can kind of work backwards from there. But for practicality's purpose, when you're just kind of evaluating stuff quickly, as the exponent goes up, you see a flattening happen. Okay, so you can compare this punching through versus this punching through here. It just goes right through, and looks like you're just kind of freehand sketching. This one right here, you're still freehand sketching, but as you approach, you're kind of tapering off. You have a flattening going on, and you want to capture that flattening with the higher and higher degree. So, for instance, if it's to the third power, it might look like this. If it's to the fifth power, you might see something like this, right? Like it gets flatter and flatter around your x to the endpoint, And if there's no power at all, then it would just be like you're just going through from whatever angle you're kind of approaching it at. But that's the general behavior that we're looking for. So let's just practice graphing this. So when you're graphing these, the first thing you want to make note of is what the degree is. And some of you might say, hey, how do I know what the degree is? It's not in standard form. Do I have to multiply in? Luckily, you don't. You just have to count how many x's you have, and keep in mind that if you were to multiply in, like that's going to be your power of x. So for instance, I've got 1x here. I've got 1x here. I should say I have a binomial here with 1x. I have a binomial here with 1x. And here I have a binomial. Now this one's actually 2x's here, right? Because it's 2x minus 5 all squared. So it's 2x minus 5 times 2x minus 5. So this has a degree of 4. Okay, so I know degrees of 4 then. Sorry, look at me. I missed this cube right here. That's a complete lie. Let's try that again. 1x, 3x, 2x's. 1 and 3 is 4. 4 and 2 is 6. So a degree of 6. Luckily, that doesn't change the general behavior because there's no difference from 4 to 6 as we're like initially sketching it out. So my degree is 6, which means it's either going to open all up, kind of like this, or open all down. So I notice that there's a negative in front, which means it's going to open down. So I don't know what the middle looks like. So I'm just going to kind of draw 2 arrows here, knowing that I'm going to connect them. And that, in the middle, I'm going to have some opening up and down, or I'm going to have some vertices and some x-intercepts and all that. But ultimately, it's going to start here and end here. So let's figure out where my x-intercepts are. So I've got an x-intercept at 3, at -2, and at 5/2. And if you're wondering how I'm getting 5/2, I'm just saying, hey, 2x minus 5 squared has to equal to 0, then square root it. 2x minus 5 has to equal to 0. X is equal to 5/2 as you isolate. So I'm just going to make note of those. So let's say 3 is right here. 5/2 is 2.5. So I'll also say that's right there, 5/2. And then I'll put -2 on this side. And I'm going to note that at 5/2, I'm bouncing. Okay, I must bounce at this one right here. And that's really the only thing I got to make note of. Oh, and that at the 2, I should see a flattening. The -2, I should see a flattening. Should get kind of flat. So let's just kind of draw that there. So I'm going to kind of draw it going flat, and I'm going to go through. And then I'm going to say, oh no, I've got to bounce. And I'm going to go through. And I'll get something like that. Okay, doesn't look very pretty, but remember, we're just kind of sketching it out, getting a vibe as to what's going on. The feature that I can easily find if I want to label it would be my y-intercept, and I would make all my x's zeros. So I could just say -3 times 2 times 5, because when I square the -5, so what's that going to be? So 25, 50, and then actually no, that's going to be 8. So 25 and 8 is what, 200? 200 times 3. So that y-intercept is actually quite high up on my axis there. So there's no real value to me labeling that. Like if you're asked for it, it's easy to find. But some of you might ask, okay, can I just find the vertices now by like saying, okay, what's in between, and then evaluating that? And unfortunately, you can't because these curves are not symmetrical like that. The vertices between any two x-intercepts are not going to be symmetrical. So without calculus or technology, we can't really find them. You can get, you can evaluate points along to get a rough idea of where they could be, but you're not going to be able to definitively say, hey, they occur at this x value here, so I can find the y value. That's why when we're sketching them, you'll often just see me kind of be lazy with my vertices and just say like, roughly in the middle there. Yeah, so that's how you would sketch these. Let me see if there's another one I want to do here. I'm just going to address some of the quirkier ones, like this right here. You would say, oh, what's that? That means I have an x-intercept at 0, and this one would be 5/2, and that one would be -3, and I've got a bounce happening there. So again, when I'm labeling, I would say, all right, 0. That's a lazy 5 over 2. 5 over 2. And then negative 3 can be over here. And I've got a bounce happening. So I'm just going to remind myself that I've got a bounce there. So 1, 2, 3, 4. So this is even. And I don't see a negative. So it must be opening upwards. And I'm just going to go through like this. Oh, got to bounce. Got to go through. And got to go through. And by the way, it should always work out perfectly as you're graphing it. Like as soon as you note your bounces, like if I didn't note that bounce, I'd go through, go through, go through, and I'd end up down here and not up there. And it'd be like, oh, geez, I did something wrong. And you want to go back and check to see if you either miscounted the X's or you didn't account for one of the bounces. Let me just scroll down here. And finally, let's do an example. I'll do this one right here. So this one, we're looking for completely factored form. And you might say, hey, it's a little bit factored, but not totally factored. And you're not wrong. All I need to do is expand it out. So I'm just going to say y is equal to x minus 1, x plus 1. And this one will be x minus 3, x plus 2. And then this tells me where the x-intercepts are. And once I have this, this is exactly like what the questions I was doing above. So I'm not going to bother going all the way through. Of course, I still want to note the degree and note that I could count the x's here, 1, 2, 3, 4. So it's a fourth degree. Or I could even go up here and say, okay, I've got a quadratic times a quadratic. So 2 and 2 would give me 4. Okay, and again, I'm adding because you might say, do I want to multiply or do I want to add Savoy with the powers? And you would say, and I know it's funny, you're multiplying the expressions, but if you think back to your exponent rules, you add the exponents. So you are going to multiply x squared times x squared here, but ultimately the 2's get added when you are applying your exponent rules. So that's why I can just literally go through and count how many x's I have to the highest degree in each expression, I should say. This is the same vibe here. I would factor out an x and I would get 3x minus 1. And again, I'd factor that and get 2x. Geez Louise, don't mess this up, Savoy. 3 must go here and 1. And then I want a negative 3 there and a positive 1. And again, I can see all my x-intercepts now. This one is a little bit trickier because you have to account for the fact that it's being squared. So x squared minus 4 is a difference of squares. So you could write this as x squared minus 4 times x squared minus 4. And the reason I'm doing that is because of that 2 there. So I'm going to have x plus 2, x minus 2, x plus 2, x minus 2. And be careful here because this is fully expanded. And this actually right here, I have 2 x plus 2's. So this is like x plus 2 squared and ditto with the x minus 2 squared. So I actually have bounces happening here and there. And I get the same thing happening here. You might say, hey, that's not factorable. I don't really care that it's not factorable. I can still find x-intercept. So you can either just solve for x like normal, or you can apply a difference of squares. I'm using quotation marks here. 3 is not a perfect square, but I can still follow that pattern. And I can say x minus the square root of 3, x plus the square root of 3. And again, I'd have 2 of them because it's x squared minus 3 squared. So again, I would have 2x minus root 3, x plus root 3. Then I would say, oh, I can write this as x minus root 3 squared, and then x plus root 3 squared. So all my x-intercepts here actually bounce. And this one will look like this. First of all, it's going to be even because I've got 2, 4, 6, 8. And then it's going to look like this the whole way through. So I've got 1, 2, 3, 4, 1, 2, 3, 4. Yeah. And of course, like some of these vertices might be higher than the others, but I don't know how to find them without some calculus or technology. And that's not for this level. All right. And finally, let's just talk about imaginary roots. There are going to be cases where you're just not going to be able to solve for x-intercepts on part of the graph. And so let's just look at this. To find imaginary roots, you just set it up like normal. So I'm just going to say, hey, x squared plus 2 has to equal 0. Well, then I get x squared is equal to negative 2. Then I would want a square root, and I get plus minus the square root of negative 2. Well, I'm going to expand that out a little bit. And I'm going to say, hey, plus minus the square root of 2 times the square root of negative 1. And I know that the square root of negative 1 we refer to as I. And by the way, some of you might say, Savoy, didn't we just use a different approach for the questions like literally 2 seconds ago? And you're not wrong. I could just say x plus root 2 and x minus root 2. Then I would say x, it's not x is equal to negative, and this should be negative root 2 in both of them. X is equal to negative root 2I. X is equal to positive root 2I. Okay, and I'm skipping the middle step with this blue stuff here because you can see it right down there. So again, any section that has just imaginary roots, you can't really do anything with them when we're graphing. If there are some roots and some are imaginary, you use the real roots to help sketch your graph, and then just fill in the rest, like fill in the curve as best you can. And that's it for graphing nth degree polynomials.